class. So today we want to look at applications of differentiation. So what do we mean by applications of differentiation? Here we mean we want to learn about the behavior of a graph of a function through the concept of differentiation. And now this has helped us to locate the maximum or minimum of functions. Okay, so when we say maximum and minimum of functions, it is a concept we use to determine uh, the shape of a graph. And this notion is mainly used in an aspect of mathematics called optimization. So optimization in mathematics help us to make the very best choice out of every situation where they like to minimize the cost of productions, or in a firm or industry where they would like to maximize the profit. Okay, so in application, these are what the maximum and minimum are all about. But here, we want to learn how to find the maximum or minimum of functions. Okay, so I'll be using uh, an arbitrary function to describe this. Okay, so let's consider an arbitrary function. F of x, okay, which is defined on the domain D Suppose we have an arbitrary function which is defined this, and this function has this behavior. Okay, so where this is measure 0, okay, so and here we also have a measure of this form. Okay, so here we have the coordinates 2, 2, and here we have the coordinates 4, 5. If you measure from here to here, this is 4, 5. So what this is telling us is that if we substitute, this is the arbitrary behavior that we are considering, arbitrary curve of a function f of x. So what this curve is telling us is that if you find f of 4 for this curve, f of 4 is equal to 5. Okay, and that is the coordinate here. And what is this? What this is telling us is that if we find, okay, this means this, okay, and this coordinate means if we find f of 2, f of 2 also means 2. Okay, so here's the curve. So these two things are telling us a certain thing about the curve that we have here. Okay, firstly, the point 2, 2 on the curve is referred to as a global minimum, okay, on the domain D that we have here. And what this is telling us is that this is a global maximum of this function f of x. Okay, so this notion cannot be described formally. Okay, when I say formally, in a form of a definition. Okay, but before that, let's also see that we'll see that at every point of x here, okay, the least among the f of x is this. Okay, and what we will see is that among this f of x that we have on the domain D, okay, all the f of x that we have here, okay, all of them are greater than or equal to f of 2, okay, and also here, all the f of x that we have here, that is computing all other points of x, okay, we'll see that the highest among them is f of 4 for all x we pick here, okay. So this is telling us about the global maximum we refer to here, that all the f of x, the maximum among them is f of 4, and in none of the f of x, the minimum among them is f of 2. Okay, so this is what we are with. So let us give the definition formally. So definition. So the first one is about global maximum. Global maximum. Okay, so let's put this in brackets. So when we say global maximum, we mean a single valued function f of x is said to have a global maximum at the point C, a particular point in the domain D. Okay, so in our illustration, this point C is being referred to as the point 4 we have earlier. Okay, so if f of x is less than f of 2, sorry, is less than f of c, okay, so if you compare this with what you have there, okay, you see that this c is this, okay, and then what you have is that the all of the f of x is less than the f of c, okay, so for all x in D, okay, so this is what we refer to as the global maximum wave function, okay, and as it is seen on the graph we have shown earlier, okay, and similarly we can give a definition for all referred to as global minimum. So let's see that. So we'll call this 1. So 2, a single value function f of x is said to have a global minimum at the point C in D if f of x, okay, is more than all f of x, okay, is more than f of c for all x in D. So this situation can be compared with the graph that we have earlier. So we'll see that all the point of x, okay, when substituted to this place, we'll see that all the value of f of x is more than the value of the minimum. Okay, so in this case, you see what is happening there is a global minimum. Okay, so another name for global maximum is absolute maximum, and for global minimum, we can also call it absolute minimum. Okay, so from these two definitions, we'll see that when we say global maximum, okay, it is when we have uh, the shape of a dome, a plain dome, okay, just like this, okay, and when we say minimum, okay, we have the plane of a valley, okay, so that is what we'll be using to differentiate the two concepts. Now, there are other uh, concept of maximum and minimum. Okay, this concept is being referred to as the local maximum or the local minimum. So let's quickly look at that also. And but before that, let us also illustrate that using a, a graph. Also consider an arbitrary curve on the plane so here we'll see that there are two maximum. There are two dome, plane dome. That is this and this. Okay, but out of the two, one is more than the other. Okay, as you can see, this the plane dome this is more than this, and because of this, we refer to this as local maximum, and this becomes the global maximum. Similarly, if you look at the plane of a valley that we have here, these are the two, and this one will go lower than this. And because of this, we refer to this point as the local minimum, while this point will be called a global minimum. Okay, so let us also illustrate this, and at the end, we'll give a kind of a summary on a graph like this. So let's call this another definition. So this definition we also to talk about the local extremum. Okay, because we want to discuss two concepts here. When we say extremum, extremum means either maximum or minimum. So one function f of x is called a local maximum at C in the if f of x is less or equal to f of c for some x in the. So as you can see, the language is changed here. Okay, for the global maximum, we use for all x, but in this case, it is for some x. Okay, not all x. Okay, so that's the major difference between them. And secondly, we also see that the function f of x is called a local minimum at C in the if f of x is greater than or equal to f of c for some x in the. Okay, so you see the tone of the definition that it has changed. Okay, so this is how we define both the local maximum and the local minimum. Okay, and we can summarize all these in a single graph. Okay, let's have the graph. So yes, let's call this a point A, point B, point C, point D, and here, okay, you will see that after the turning point, okay, instead of the curve to come down, okay, it goes up again. Okay, so let's call this the point E. Okay, so in the summary we have here, so this curve is an arbitrary curve. Okay, and, let's call it f of x. So this point E accordingly is referred to as the point E here is a local maximum. Okay, so the point B here is a global. The point B is a global minimum. Okay, and the point C, as we have it here, is also a global maximum. And the point D is a local minimum. Okay, so these are what we have. So now the point E, we observe that the tangent line is almost horizontal on E. Okay, and this is so because if you look at other maximum value that we have, immediately after the point A, okay, the curve decreases. Similarly for this, but for this, immediately after the point, okay, this maintains a certain horizontal fall, and then after that it goes up. Okay, so we call this point E uh, uh, that this point E is neither a maximum value or nor a minimum value. And in this case, we call this point the point of inflection. Okay, so let me come again. The point E is neither maximum nor minimum. And in this case, we say E is a point of inflection. Okay, so that is that on the summary on the extremum value of functions. Now let us now give a theorem. Okay, that is what must happen before we can say a function has extremum value. So theorem. So this theorem says if f of s, that is a function, has okay, what we say local here, okay, it's also valid for global, but we say local because in order not to fall into an ambiguity. So if f of s has local extremum, okay, at the point C in a given interval, and f prime of x or f prime of c exists. Okay, so what this is saying is that the slope at c must be 0. Okay, so this theorem is actually telling us the condition under which if a function has local extremum, okay, and then we have that if the derivative at that point exists, okay, so the slope of that function is actually 0, okay, and it means in that case at the point C, the slope will be horizontal, okay, or let's say it will be parallel with the x-axis. Okay, as you can see, let's just give you a case here. Okay, so if I have a curve with turning point is this. Okay, so this the tangent line, okay, which is the slope here. Okay, you see it is parallel to the x-axis, and in this case, if it is parallel, it means there is no sloping, and in that case, the tangent here is 0. Okay, so that is what the theorem is saying here. So in this case, there is more to this point C, and of course, this point C is located at somewhere here. Okay, so in this case, this point C is called a critical number. It's called a critical number, or simply a critical point. Okay, so in some text, you will see this point as a turning point, or a stationary point, or extreme point. So that we call this point C. Okay, so let us now see a few examples of a function that has a extreme point like this, and later we'll consider the condition under which a function is either maximum or minimum. So let's say example of this. So we have to find the critical number. The function f of x equal to x squared minus 4x plus 1. Okay, so here we are going to apply the theorem we just state. Okay, so that's a solution. So here we are given f of x to be x squared minus 4x plus 1. Okay, according to the theorem, for this function to have a relative extremum, okay, we have said that derivative must also exist. Okay, so at the critical point, okay, which is f prime of c must be 0. Okay, so this simply means f prime of c, that is, if you look at this, this is a derivative, but at point c, this 2x minus 4 must be 0. So this simply means this. Okay, so wherever you see x, you replace it with c. And at that point, it should be 0. Okay, so accordingly, okay, we need to find the critical point from this equation. 2c minus 4 equals 0. Okay, this implies, we'll make c a formula. Okay, this will be equal to 4 divided by 2. Okay, when 4 goes there, then divide both sides by the coefficient of c, and then we'll see that the critical point, okay, is 2. Okay, so another example under this, okay, the example now we can find the critical point of a function. Okay, so here, if you are given a function f of s equal to this minus 2x cubed plus 3x, okay, or okay, so this is okay. So if I give a function like this, okay, so as you can see, this is a cubic polynomial or a cubic function. Okay, so we want to find the critical number of this point, and of course, yeah, this will have a two critical numbers. Okay, so solution. So we are given f of x equal to 3x cubed minus 2x raised to the power of 2 plus 3x minus 2. Again, according to the theorem, if you find the first derivative of this, okay, so this will be x squared minus 4x plus 3. Okay, so at the critical point, so f prime of c will be 0, and the meaning of this is this: f prime of c is equal to c squared minus 4c plus 3, okay, equals 0. Okay, so the derivative here is a quadratic equation, and this means c we have two roots, or the equation we have two roots, okay, which are equivalent to the turning point or the critical number we are referring to. So in order to solve this, okay, one can adopt the method of a factorization method. Okay, so and this will be, let's take this off. So here we have c squared minus 4c plus 3 equals 0. So if we use factorization method, this will be c squared minus c minus 3c, okay, plus 3 equals 0. So this will be c into, okay, we are grouping this term into two. Okay, and this will be this will be c minus 1. Okay, again, negative 3 is common here. This will be c minus 1 equals 0. Okay, so c minus 1 is common here, so we can factor that out. And then we are left with c minus 3 equals 0. Okay, accordingly, this is a product of two terms equal to 0. Okay, and this situation means that c minus 1 is equal to 0 or c minus 3 is equal to 0. Okay, yeah, this implies, okay, let's refer to this as the first critical point, and it is equal to 1. Okay, and you will see all c2 as the second critical point is 3. Okay, so therefore the critical point of the function is 1 and 3. Okay, accordingly. So this is how we find the critical point of a number or of a function. And don't forget, anytime we have a curve, okay, that's usually a turning point. Okay, if this graph is representing what we have there, okay, so this is like this. Okay, this means the first turning point, which is C1, and second turning point, which is C2. Okay, so this is how we do that. Okay, so let's give some exercises under this, and then we can move further ahead to go to text of extremum function. So we will find the critical numbers for the following. So number 1, okay, the function f of s equal to sine x. Okay, because this sine s is a transcendental functions, so it has many turning points. Okay, so let us restrict the x in between negative 2 pi. So this, okay, find the critical numbers of this function between negative 2 pi and 2 pi. So 2. So let's find a quadratic function f of x equal to 1/4 x raised to the power of 4 minus 2x cubed plus 11/2x squared plus minus 6x plus 1. Okay,